Introduction to and coded demonstration of Pollard factorization. Pollard factorization is an integer factorization method for composite inputs. In essence, given some integer, Pollard's algorithm outputs a prime factor of that integer. You can immediately see how this would be useful in factoring at least small semiprimes within the framework of toy RSA encryption examples. We can use Pollard's algorithm to find one factor of some semiprime that we're interested in factoring, and then simply divide the semiprime by the found factor to obtain the full factorization of the semiprime. Pollard's factorization is by no means the fastest factoring algorithm out there, but it's far superior to, say, a naive trial division algorithm. I'm going to start off by just working through a quick paper and pencil example wherein I try to factor the input n is equal to 9,991, just to give you the gist of how the algorithm works. The first step is to choose sum a1 greater than 1. So in this case, I'll just define a1 is equal to 7. Now I'm going to compute the GCD of n and a1, which is equal to the GCD of 9,991 and 7, which is equal to 1. So I'm going to define a new variable a2 is equal to a1 squared mod n, which is equal to 7 squared mod 9,991, which is equal to 7 squared, which is 49. Now I'm going to find the GCD of n and a2 minus 1, which is equal to the GCD of 9,991 and 49 minus 1, so 48, which is equal to 1. So I'm going to again define a new variable a3 this time is equal to a2 cubed mod n, which is equal to 49 cubed mod 9,991, which is equal to 7,748. I'm going to go through this again and find the GCD of n and a3 minus 1, which is equal to the GCD of 9,991 and 7,747, and this is equal to 1, so I'm going to define a new variable a4 is equal to a3 to the 4th mod n, which is equal to 7,748 to the 4th power mod 9,991, which is equal to 9,775. And so I could keep on going here, but the idea is that so long as the GCD of my input n and the preceding a sub I that I've defined minus 1 is equal to 1, then I'm just going to keep on defining new a sub i's by taking the previous a sub I and raising it to an exponent that increments by 1 with each iteration, and then taking the modulus n of the result of that exponentiation. And whatever the result of that is my new a sub I. And so what I'm eventually going to end up with is the GCD of 9,991 and 8,730 is equal to 97, which of course does not equal 1. And so I know that 97 must be a factor of 9,991. And sure enough, when I divide 9,991 by 97, I get 103. And so I know that the full factorization of 9,991 must be 103 times 97. What I would like to do now is program this process so that given some semiprime input n, I use Pollard's algorithm to obtain the two prime factors of that semiprime. I'm going to be working in R here, and so the first thing that I want to do is make sure that I'm using the library Pragma. And this is just going to give me access to both the GCD and modulus functions. So next I'm going to define an initial value of a. I'll call it a initial. And I'm going to set it equal to 7. I'm also going to create a variable to represent my exponent, call it exp, and I'm going to initially set it equal to 2. So now I'm ready to create my function. I'll call it Pollard Factorization, and it'll take as input my semi-prime value of n. Now I want to do an initial pass-through to determine if by chance my initial value of a initial happens to evenly divide my input n. So I'm going to handle first the case in which a initial does not evenly divide n. So that'll happen if the GCD of n and a initial is equal to 1. And if that happens, I'm going to define a variable a to be equal to a initial raised to my exponent exp, and then I want this exponentiation modulus n, so I'm going to say mod this and n, and so this just translates to a initial raised to my exponent mod n. And this is equals equals, not just equals. And then otherwise, so if a initial does not happen to divide n evenly, then I'm just going to define a to be equal to a initial plus 1. And so this if else handles this initial step right here. The only step where I'm finding the GCD of n and a sub I, not a sub I minus 1. And so now I'm going to handle the more generic remainder of the Pollard algorithm. So first thing that I'm going to do is just increment exp, since the above is already going to have handled the case for my exponent is equal to 2. And then I'm going to create a while loop and say that while the GCD of n and a minus 1 is equals to 1, then I'm going to define a is equal to a raised to my exponent exp mod n, and I'm going to again increment my exponent. And it's just that simple. This while loop is going to handle the execution for the rest of my steps. I'm going to hop outside this while loop now and define a new variable, factor 1, that I'm going to set equal to the GCD of n and a minus 1. And incidentally, in case you were wondering, this is why I defined up here a to be the initial value of a plus 1 in my initial pass-through, so that I ultimately obtain the GCD of n and a minus 1 plus 1, which is equal to a, as one of my factors in the case that a initial divided n evenly. I needed to define factor 1 in such a way that made sense in either case, so either if a initial divided n evenly or if it didn't. And so now I'm going to define factor 2 is equal to n divided by factor 1. So finally, I'm going to create a vector of factors. I'm going to put factor 1 and factor 2 in here. And I'm just going to return the factors. So let's go ahead and try to test this out. I'm going to source this, and then I'm going to call my function Pollard Factorization, and let's try 583 to try to factor. This is a semi-prime. And so I get the factors of 11 and 53, and sure enough, that's 583. So then let's try out 3,233, let's say. Okay, so I get factors of 61 and 53, and let's just check, 61 and 53. Perfect, 3,233. And so then the initial example that I started out with was 9,991, I believe. So let's try that for 9,991. And I get factors, yep, of 103 and 97, just like I got up here. So then how about one where A initial will divide N evenly? So I have A initial is equal to 7. So let's try 7 times another prime factor, 13, is 91. Okay, so then let's try factoring that with our function, 91. And great, we get 7 and 13. So we get the correct factorization. So I want to emphasize here that the function that I've written works specifically for semi-prime inputs of n, just because that's what I'd primarily be interested in using Pollards for. But you could probably pretty easily extend this to work for non-semi-prime inputs too. Well, as always, I hope this was helpful, and thank you for listening.